All right. So we're doing NP reductions. All right. And I'm going to start and review what we've done already. That way, and I'll do it fast, but if you see anything you don't understand, holler. All right. So we're going to have two problems. We're going to have the clause set problem, and we're going to have the puzzle card problem. And what we're going to try to prove is that if you have an algorithm for the puzzle problem, then you have an algorithm for clause sat problem. All right. So what's the clause problem? The input is the and of clauses, and each clause is the or of literals, and each literal is a variable or its negation. And a solution assigns a value to each variable. And when is it satisfiable? Right, it's satisfiable if each clause has a literal that satisfies it. And how does the literal satisfy it? Is either the literal is not negated, right here the B is true, so it satisfies that. Well, here the D is false, so the not D satisfies that clause, right? And what's our first order logic statement? Is that we want to say the instance, right? These clauses are satisfiable if there exists a solution, if there exists a setting of the variables that satisfies what? It satisfies every clause. And how does it satisfy every clause? For every clause, there has to exist a variable that's satisfied. And how does the variable get satisfied? Well, if in the instance the variable is unnegated, like this B, and you set B to be true, then that B is satisfied and it satisfies the clause. Or here the C is false, so here C is negated, so that satisfies the not C, which satisfies that clause. So we're saying the clauses are satisfiable if there exists a solution that satisfies every clause, because for each clause there's a variable that is either negated and negated in the right way. Everybody understand that? So what's the clause puzzle? The clause puzzle is you're given a bunch of cards with each card has 2 columns and lots of rows and a box. And what you do is you take a solution is you take cards and you flip them left to right. So I remember I had my C card flipped was wrong. I had a hole here, but I fixed that. So now you take this card here, you flipped it left to right, and you have a proper flipping of the card. And what happens is you flip them in various ways so that when you stack them all up, it covers all the X's. All right. And so what are we saying? A set of cards is satisfiable if you can cover all the X's. And what does that mean? It means there exists a solution, a way of flipping the cards that covers all the X's. And there's a way of flipping it. And what does that mean? That means there exists a solution such that for every row, there exists a card that covers it. And how does it cover it? Either it's not flipped and the left is a non-hole, or it is flipped and the right is a non-hole. Everybody understand the two problems? So what is our goal? Is we're going to assume that we already know, Cook already proved that the clause sat problem is likely not in polytime, right? So we want to prove that the card problem is not likely in polytime. And how do we do it? Well, we is by sort of proof by contradiction, we assume that the card problem is in polytime. And if it's in polytime, then we have an algorithm for it. and we can design an algorithm for the card problem, for the clause problem, using the card problem as a subroutine. And that gives us that the clause problem is satisfiable, but it has polytime algorithm, but we don't believe it does, right? We believe A is not true. There's not a polytime for the clause problem, and hence there's not a polytime for the card problem. Everybody get that? So the proof, hopefully you can follow these proofs. You can meditate and not get too stressed. What we're going to do is we're going to make a mapping between these two problems. All right. Now the mapping, the instance only goes in one direction. All right. It happens to be a bijection. In this case, it happens to be a bijection, but it's not always a bijection. All right. So given a bunch, right, because we're assuming we have an oracle that will solve the clause problem. So we're given a bunch of clauses, and we have to give something to, we're trying to come up with an algorithm for the clause problem. So we're given a bunch of clauses, and we have an oracle for the card problem. So we have to produce a bunch of cards. And how will we do it? Well, we have our clauses have a bunch of variables, and we will make a card for each variable, right? We have variables A, B, C. We have cards A, B, C. And then let's consider a particular variable, and we have to decide, right, that card will be labeled C on the one side, and its flip side will be labeled not C. Right, so now we have to decide where to put the holes. So for each clause, remember we were given a bunch of clauses. So each clause we will have a row of our card, right? And now consider a particular variable and a particular clause, right? So here's variable A appears positively in this first clause. So since it appears positively, we'll take the card A, because we're talking about variable A, and we will put a non-hole on the left. Why? Because setting A to be true will satisfy this clause, and not flipping A will cover this X, right? So the point is that this non-hole is going to cover the X, just as setting a variable true will satisfy the clause, right? Now let's look at the second clause. It has a not A. So in the not A, we will put a non-hole in the right column, right? And why is that? Because if we set the variable to be false, it'll satisfy the clause. And if we flip the card, then the not hole will go over and cover the X, right? Everybody buy that? So as
Yes.
a sort of a, yeah?
Yep. Just confirm.
All right, so now we get a mapping between the solutions, and this mapping does need to be a bijection, all right? Or at least it's easier if it's a bijection. It doesn't have to be a bijection, but ours is. All right, so here, that's what I'm just saying, it's a bijection. Basically, if a variable is said to be true in the solution, then we'll flip the card. And if the variable is set to be false, oh, sorry, if the variable is true, we don't flip the card. And if the variable is false, we do flip the card, and vice versa. Right, does that make sense?
Yep.
All right. Now, what is the algorithm going to be? Well, we have an oracle to solve the card problem. So we're given a bunch of cards. If you give the oracle cards, the oracle will tell you what the solution is. You know, how to flip the cards. And if there's not a solution, she will say, no, there's not a solution. And so what we want to come up with is an algorithm that solves the clause problem, right? So we're given a bunch of clauses, and we want to know, is there a setting of the variables that satisfies them all, right? There's such a delay in these two screens. Anyway, so everybody's fine. So now, how do we design our algorithm? We're given a bunch of clauses. As we described, we convert those clauses into a bunch of cards. We ask the oracle for the solution for those cards, and we give the same answer. Right? Everybody follow that?
Yes.
Sir.
Yep.
So when we're you see how there's the clauses, right? So
Yep.
all we're doing with the clauses is pretty much like stacking it on top of the box so that the X's get covered, correct? Is that what you're trying to say?
I don't like what you said, because it sounds like you're talking about covering the X's, so it sounds like you're talking about the solution and how you're stacking them. All we're doing is from the clauses, we make cards. We don't say how we're going to flip them or how we're going to put them in the box. That's the job of the oracle.
Okay.
What we say is for every variable we have a card. For every clause we have a row. Does that make sense?
So then, for example, for the first clause that we have there, that'd be row 1?
Yes. Right?
Okay.
See, if you look at row 1, if you follow along row 1, A has a non-hole in row 1, there's an A that's not negated. So row 1 has a non-hole in the A card, and B has a negated B. So the first row has a non-hole in the right hole of B.
Okay.
Right? And
so do we not look at C at that point because we kind of have what we need, or?
You know, this example is not this was our example.
Okay.
Right? That's where the cards came from.
Mm-hmm.
Right? Here, A, non-hole. B is flipped, so non-hole in B. D is not flipped, so non-hole in D. Right?
Okay.
In here, once we got to here, I wasn't expecting people to read the holes.
Okay.
And right? And I couldn't make this longer. I made this shorter. So
Okay. The first example was just kind of stating that therefore in that row it will always be covered, correct?
No, we haven't said anything about that. All we do, okay. You're getting ahead.
Okay.
Right? That's what we're going to have to do next, is we're going to have to prove this algorithm works.
Okay.
But for now, we're just telling what the algorithm is. Right? For now, we're giving these clauses. We make these cards. We take these cards. We give them to the oracle. The oracle gives us a yes, no. We say yes, no.
Okay.
Right?
All right.
So now our job is to prove that the oracle works. Right? So that's what the algorithm is. Now, what our job is to prove that for every input of the clause problem, the answer to the SAT, right? For every instance of the clause problem, it's satisfiable if and only if the corresponding cards are satisfiable.
Okay.
Right? This says for every set of clauses, the clauses are satisfiable if and only if the corresponding cards are satisfiable. Right?
Okay.
And why that will prove that our algorithm works. Right? Why? Because what do we have to do to prove our algorithm works? We have to prove that for an arbitrary bunch of clauses, the algorithm says yes, if and only if that's the required answer. Right? That's the definition of an algorithm working. And what is that? Well, we require the instance requires a yes if and only if the clause is satisfiable, right? That's just the definition of our problem. And what do we need up here? What do we need? We need that the clauses are satisfiable if and only if the card's satisfiable. That's what we just proved up there. Well, we'll prove. And then what does the oracle do? The oracle will say yes, even if and only if the cards you give it are satisfiable, right? And what does our algorithm do? Our algorithm says yes, if and only if the oracle says yes. Right? Does that make sense?
Yeah, it does.
So now we have our first order logic statement that we're going to prove, right? And those people who are in 1090 have an advantage because you're now experts at proving first order logic statements. The rest of you suffered in test 1. All right, so now let's see if we can. So this is an if and only if. So really we would have to prove it in both directions. All right, but actually it's a pretty easy that the if and only if goes in both directions, but the standard thing is we just go in one direction. All right, so well, I mean we have to go in both directions, but we're going to do one of them. All right, so we're going to prove this. What we're going to prove is you give me an arbitrary set of clauses. You map those clauses over to a bunch of cards, and you assume that those cards are satisfiable. Then that gives me that the clauses are satisfiable. All right? Everybody ready to prove that? So how do you do it? Well, actually, this slide is wrong because we have to start with the adversary giving me arbitrary clauses, right? So let's pretend we had an adversary here that gave us a bunch of clauses, right? Adversary gives me some clauses, and what do I do with my clauses? I map them over to some cards, and then let's assume A is true, all right? So we're assuming that we have an oracle that reassures us that our cards are satisfiable, right? And then our goal is to prove that the clauses are satisfiable, right? And we're going to get help from the oracle, all right? So, here, that was just the running of the game. Now we're ready to do it. Now that was just a reminder of who's doing what, right? If you needed a reminder of who's doing what, I'm proving, the blue guy's proving things, the oracle's helping, and the red guy, so the blue guy comes up with exists, and the red guy comes up with for all, if you didn't remember that. All right, so that was just a reminder, not the game itself. Let's now do the game. We have a for all. So who goes, how do you prove for all? You have the adversary give you an arbitrary set of clauses. All right, so there's a bunch of clauses. And what do we do with our clauses? There's all our clauses. They're not all written down here because they didn't fit there, but there's our clauses. And what we're going to do with our clauses is we're going to use our mapping to map them over to a bunch of cards, right? Everybody remember how we build our cards? Right, so now we have clauses that were given to us by the adversary, and we have the corresponding cards. Okay, great. Now we're assuming the left-hand side, right? So the oracle up here is promising us that the cards are satisfiable. And what does it mean for the cards to be satisfiable? It means there exists a way of flipping the cards that says that for every row, there is a card that covers that X, right? That's what it means. And that's what she's promising us, right? All right, and what is our goal? Our goal is to prove that the clauses are satisfiable, right? How do we prove the clauses are satisfiable? Well, what are we saying? We're saying that there exists an assignment to the variables such that for every clause, one of the variables is in the clause is satisfied, right? Everybody get that? So that's what we have to prove. So I just got, right? So how do we prove it? We start with there exists, right? I have to prove that there exists an assignment. Now, how am I going to come up with an assignment to my clauses, right? Who can help me come up with an assignment?
The card puzzle from the Oracle.
I got the Oracle, right? I go over and talk to the Oracle. What can the Oracle do? She says that she's promising me that there exists a solution to the card problem, right? It tells me how to flip each card. So let's see what she's got for me, right? There it is. There's the cards flipped. She promised me that there was a way to flip all the cards. And I said, great, give it to me. And she gave it to me, right? And so what am I going to do now? Right? I have to come up with an assignment to the variables, right? I have to say for every variable whether it said it to be true or not. How am I going to do that? Right? She told me what? She told me, don't flip A. So what value should I give A?
True.
True. She told me to flip C. So I set C to be false, right? There, right? I do this mapping here, and it gives me the variables, a solution to the variables, right? Everybody buy that? So now I'm claiming that there exists a solution to the variables, but now I have a solution, so I just have to prove that it has the right properties, right? So let's move along. What do we have to prove? We have to prove that the setting of my variables satisfies every clause, right? So how do I deal with the for all clauses?
Adversary?
Adversary, exactly. The adversary comes and tells me some clause, right? So this is the clause now that I care about, right? The adversary said, I care about that clause, all right? All right, so what am I going to do now?
The prover chooses X.
Yes, I will have to come up with an X. I will have to come up with an X. Very good. But before I come up with the X, let's see if we can get some more help from the Oracle. What is the Oracle saying? She's saying, right, she gave us this exist thing, and she's saying for all rows something is true, right? So we can tell her any row, and she will promise us something about that row, right? So which row should I ask her about? Right? Yeah, I'm going to ask her about the clause in question. The clause that my adversary gave me, the red clause, corresponds to some row, right? Remember, there was a one-to-one mapping between clauses and rows, right? So she's going to give me some row. And so now we know we have a row in mind, right? We have a clause in mind. We have a row in mind. We have a set of cards, a solution for the card problem, a solution for the clause problem. And now we can move along. In fact, she says it's true for all rows, right? She's promising it's true for all rows. So there's something true about this row, right? What's true about this row is that there exists a card, right? So now let's go back to what we have to do. Our goal is to come up with a variable. How am I going to come up with a variable? Right? Let's go back to our oracle. What can our oracle do for us? She's promising us that there exists a card. So we say, hey, tell me which card you mean. And we're going to call the card she talks about Z, but right now that card is B, but sometimes it'll be a different card. Depends on what we're doing. But right now she's telling us about card B, right? So our goal is to come up with a variable. Which variable should we talk about? I have to just come, right? If she's telling me something about card B has to do with variable B, right? So it's reasonable that I'm going to talk about, right? In fact, she's promising me something. Let's go back to what she's promising. She gave me a card B, and she's promising that the card B covers the X in the row we care about, right? So that's pretty useful. Here we say, see there, it's covering it. Or maybe here's a choice. She had a choice here. Maybe she told us about card C, because card C has been flipped. And when you flip card C, it also covers that X in the row we care about, right? So it happens that she has a choice when she tells us there exists a card C that covers the X. Actually, in this case, it happens to be that there are two cards, right? You can see card B not flipped covers the X, and card C, when you because we flipped it, it covers the X, right? People see that? So when we ask her about a card, she has a choice to which one she gives us. She either tells us card B or card C. Either way, we have to come up with an X. We have to come up with a variable. So which variable are we going to come up with? Well, if she names card B, we're going to name variable B. And if she names card C, we're going to name variable C. Right? Does that make sense? All right. So now we have all our objects. And what we have to prove is we have to prove that this assignment of the variables, right? We have an assignment of the variables, and we have a clause that we care about, and now we have a variable that we care about, right? We're caring about the third clause and the variable B. And we have to make sure that the setting of the value of B it satisfies the variable B. And you can see in this case it does, right? B is set to be true, and there's a B here, so that B satisfies the clause, right? Everybody follow what we're proving? And now we want to prove that that's always the case, all right? We need to prove that however this game played out, that no matter what, the setting of the variables we have will cover the card the variable we talked about will satisfy the clause that we talked about. All right. So how are we going to prove it? Again, we're going to have help from our oracle. Like we're not working all by ourselves here. The oracle gave us various information, and the oracle is promising us that the card covers the X in the given row, right? All right, so now when I first had a proof like this, and I had this on a test, and everybody got lost with this part, all right? And then I tried to make slides, and the slides were too complicated, all right? So I've made a little table here, and I think our table will help us. So a table is going to try to talk about all the various universes that there might be. All right? So, and I'm saying that there are 2 to the 4 cases. The first case is, let's consider the clauses and our given instance here. And, right? Remember, we're talking about, we have a particular variable in mind, a particular clause in mind, and we have our input, and we want, and what is that variable? That variable in that clause, there are 2 cases. The variable we're talking about in the clause we're talking about might be negated in the input, and it might not be, and it might be unnegated in the input, right? So that's, everybody see those 2 cases? It's talking about the something about the input, something about right, the input to clause sat, our variable may be negated or not. All right, let's go down here and say something about our solution for the clause problem, right? Our variable in question, we have a variable b in question, and it may be set to be true and it may be set to be false, right? Those are 2 possibilities. Everybody got that? Right? Now, again, let's go to the card problem. And we have a particular set of cards, and we have a particular card we're talking about, and there are 2 cases. There might be a hole in the left of the column that we care about, right? We have a card we care about, we have a column we care about, a row we care about, and that card in that row might have its variable set, you know, it might have a non-hole in the left and it might have a non-hole in the right. I guess it could also have a non-hole anywhere or a non-hole both places, but that's probably not going to happen. So now let's talk about the solution, right? We have a particular card and we have a solution. Well, that card might be flipped and it might not be flipped, right? Everybody see all these situations? Right, we played the game. What was our game? The oracle gave us, the adversary gave us adversary gave us a bunch of clauses. So that gave us our input to the clauses. We mapped that over to the oracle, over to the card problem to give us a bunch of cards, right? Then the oracle gave us a solution to the cards, and we came up with the solution to the clauses. And then the adversary gave us a clause. And we gave that clause to the card problem, which specified a row. And then the oracle gave us a clause. Sorry, the oracle gave us a card, and that gave us a variable. Anyway, so now we have all these various cases. All right, so we're going to narrow these cases down. There's way too many cases here. So let's first look at, we're going to try to narrow all the cases down to 2 cases. Well, here, here's one case. Suppose the card has a non-hole in the left and we don't flip the card. Right, so here's an example, card B, we didn't flip it and it has a non-hole in the left. What does that tell us? Oh, look it covers the X, right? So in this case where we have top green, that covers the X. Let's look at another case. Suppose here we have this card, it is flipped, and it has a non-hole on the right, right? So when you flip it, see it had a non-hole on the right, and we flipped it, and then it covers the X, right? So in this case, when we're bottom, it covers the X, right? Now, what about these other weird cases? Well, if you do that case, it doesn't cover. See, it doesn't cover. In that case, it doesn't cover. Right? Does that make sense? So what do we know? We're knowing that the oracle promised that the card she mentioned covers the row we mentioned, right? The column we mentioned, yeah, the row we mentioned, right? So she promised that. So that eliminates these two possibilities, right? Does that make sense?
Yes.
What do we know? So that's, here I put it, this if and only if. What does the if and only if mean? This little red arrow, it means we're at the top if and only if we're in the top. We're in the bottom if and only if we're in the bottom. Right? Does that make sense?
It does. Sir, on the table, do we write like every single situation that we will have between those two cases, card and other problem?
Well, this is the first time I've ever used a table like this.
Actually, it's a really good explanation. I just want to fully understand how the table we should build when we see the problem.
Well, at the fear of generalizing to all the problems in the universe, I'm going to say that maybe this table generally, it might be a good table because what are the there are 4 squares.
Yes.
Right? There's the input to the clause problem, and what's the situation there? And likely there's only, usually we do things binary, so there's likely 2 situations.
Yes.
Right? And then there's the solution to the clause problem, right? So likely there's 2 situations. And then there's the input to the card problem. There's likely 2, and the input. So in our, hypothetically, if you have to do one of these on Friday, which there's a good chance, you will have 2 problems, right?
Compare. Okay.
They will be different. They'll probably be different problems, but there'll be some problem and some problem. And each of them will have an input and a solution.
Okay.
Right? So you can imagine making these 4 squares. And then for each of them, given the setting that we have for the game, there'll be 2 situations.
Okay.
Right? And so then that will give us 2 times 2 times 2 times 2, 2 to the 4 possibilities, and you'll have to narrow them down.
Okay.
Right?
Okay.
And I think the way you narrow them down will be very similar. Right? Over in the card problem world, right, we know that there's a link between its solution, its input and its solution. Why do we have a link here? We have a link here because we've promised that the solution to the card problem covers all the x's, right? So that gives us this link here, right? We have this link between the card's instance and the card solution because it's promised to be a good solution. Are you guys still there?
Yes.
Good. My other laptop crashes and it makes me worried. All right, so now let's find some more links. Remember, we had a bunch of an instance to the clause problem, and we mapped it over to an instance to the card problem, right? And how did we do it? We did it such that if the variable, right, here what do we say? If the variable appears positively in the clause we care about, then we put a non-hole on the left side, right? So that says if it's not negated, then there's a non-hole on the left side. And we said, well, if the variable is negated, then we put a non-hole on the right side, right? So this mapping says that if you're on the top, you're on the top. If you're on the bottom, you're on the bottom, right? Does that make sense?
Yeah.
And what about our solutions? Remember, we had a mapping between the solutions. The card people gave us a solution. We mapped it over to a solution for the clause thing. And what was the mapping? Well, if the variable is negated, then we flipped it. And if it wasn't negated, right, if the variable was false, right? Here we have this mapping here, right? If the variable is true, then we don't flip, and if it's false, we flip. Right? Does that make sense? So we have these if and only ifs here. Right? Everybody follow each of these?
Yes.
All right, and what does that give us? That gives us we can go around the box, right? And that tells us that so there are two cases. If we're in the top, right? If this is top, then this is top, then this is top, so this is top. If and only if, right? So now that tells us, well, if the variable is not negated, then it's set to be true, right? And hence it's satisfied, right? That satisfies the clause. And what about these bottom guys? If the variable is negated and we set the variable to be false, then that also satisfies the clause, right? So the conclusion is that we've satisfied the clause, right? So we proved that, right? We proved that our set of clauses, we were given a bunch of clauses from the adversary, and we proved it was satisfiable. Why? Because we came up with a setting that satisfied every clause, right? Everybody good with that? And so what was the big picture is that we're trying to prove that what we tried to prove is that the clause problem isn't harder than the card problem. Why? Because if we had an algorithm for the card problem, then we would have an algorithm for the clause problem, right? But our belief is that, right? Our belief is that we don't have an algorithm for the clause problem, so we don't have an algorithm for the clause problem, right? We believe that the clause problem is hard, but the card problem is at least as hard, right? See here, we put card problem above clause problem. Everybody get that?
Mhm.
And that makes them both what we call NP complete. Everybody good?
So I just want to understand the function of the oracle better. So is the oracle just the assumption that card map I is true? It's just that whatever we're trying to prove, that's what it is? Okay.
Yeah, yeah, exactly. Yeah, if you come back to the game here, where is our game? Right, so let's just review the game here, right? We're given a bunch of clauses that we need to solve. Who gives them to them? Some adversary gives them to us. And what we do is we take those clauses and we map them over to some cards. And then the oracle promises us that those cards are satisfiable. And then we have to prove that the clauses are satisfiable.
Okay, so we like we're doing what we're doing is we're proving the B implies A, and then because we know not A implies not B, like modus ponens, we get not A.
Yeah, that's at a higher level. So here what we're proving is that for every input, if the cards, if the oracle says yes, right? Then we will also then we'll also be able to, if her answer is, if the oracle's answer is a yes, then our answer will also be a yes. Now we have to also prove the other direction, right? So when we're proving the game, you have to Here, we have to for every bunch of clauses, we also have to prove that if the clauses are satisfiable, then the cards are satisfiable. And that proof is that pretty much identical. It just, you flip the roles of the people.
Right. So given a particular reduction, like in this case, we would only need to prove the one way, right? We'd only need to prove clause
No.
that implies no.
If you were doing the full thing, you would have to prove it in both directions. Right? Because here I want to prove that my algorithm works. Well, I need to prove both, right? I have to both prove that if the input, the yes input, that the algorithm will say yes. And I also have to prove if my input is a no input, then my algorithm will say no. And how do I do that one? I say, well, if the algorithm says yes, then the input's a yes. And if the input's a yes, then the algorithm says yes. That's where the if and only, that's where this if and only if comes in. Right? I mean, you can imagine I could do a reduction where I take my bunch of clauses and I map them to some really silly set of cards that are always satisfiable, right? They have no holes whatsoever, right? Now, did I prove anything? Well, clearly not. I didn't do anything smart, but I would have that the cards are satisfiable. Why? Because I always give satisfiable cards. So the oracle these will always be satisfiable, but so when these, right? But you might get the mapping one way, but not the other way. Or I guess really in that case, I make my cards so that they're never satisfiable, right? So if they're never satisfiable, then this is a no. So this would be a no as well. I don't know. You need it to go in both directions. Does that make sense?
I think I still need to think about it more, but
All right.
like, yeah, I don't want to hold up the class.
Well, I'm sure everybody's. Let me tell you, I have been trying my best to teach this for decades, and I've had many different types of slides. And if you want more, you can go to. I have whole sets of slides on reductions, and it would be good if you looked at the other ones as well, because then you could say which ones you like better. This one focuses much more on the logic. Anyway, any more questions about that?
Professor, I had a
Yeah.
question. So in the clause set, if we directly find out the solution and reverse engineer from that, would it be okay? Like by using the truth table, we can find out where the clauses are acceptable to find which values are true and which values are false. And then from there, we can try flipping the cards accordingly.
No, because you're needing to prove that it works for every set of clauses, right? So the adversary is giving you some really nasty set of clauses, and you have to prove that your algorithm works then. And so you won't even know, when you're doing the assignment, you won't even know what the example is. I might give you some examples, but that's just an example. You have to prove it works for every example.
So will the cards will be given to us or not in the test?
Well, I will give you it would be a different problem. And if it were the card problem, I would give you an example of cards, but that's not, but you have to prove that it's true for every example.
Okay, not sure it's clearly again. All right, thank you.
Right, the adversary will give you an arbitrary set, and you need to deal with it.